careful. I will be morning today. Did you fill up the hours thing yet? I'll do today. I planned on the weekend. Yeah, come on. It flew by. I'll text you in my number because I need that to get set up. It's supposed to be sometime this week. It's like why one of her your body's like, we do it every day. Well, you're talking like sign the paper and send it back, or I guess you have to fill it out. Yeah. I said to sign it. I only call it that. It's
Did anyone get the LCD to work?
We went into a board stage in that software.
Yeah. Because where?
Like into a board stage.
Okay. So it looks like a software error. Okay. I have not had a chance to take a look at it, so I will try and get a chance to take a look at it. I'll give you a little more time to, well, I'll go through the software setup again because I think not everyone got that. I'll give you a little more time to work on it, maybe do a little debugging on it today. We are kind of wrapping up, actually. So we're going to look at, in the rest of this chapter, we'll discuss interfacing to other types of devices, in particular, looking at motors, solenoids, relays. The next course that you'll take in the spring, 454, you spend that whole semester actually interfacing to all these different devices. I believe what they did last spring, I think Professor Randall intends to do the same thing this spring, is actually do all that in the process of building a robot. So interfacing to all the different motors and sensors that you need to interface to as part of this robot kit that he has. I haven't talked to him, but I think that's the plan. And it actually uses, the reason I'm using this microcontroller in Code Composer Studio is that's the same software development environment and processor that he used last year in the course. So I'm pretty sure he plans to use the same stuff again. I'm trying to get an update on the COVID stuff to see if we, they haven't updated it. So I will try and see if we've got enough maybe relays so that you can go through the process of interfacing to a relay. But some other interfaces that you may encounter that you want to hook up to your microcontroller. One is what's known as a scanned keyboard interface. And these are really cheap keyboards. They're typically like touchpad keyboards for like you might see for a phone, or just 16 key keyboards. Now, typically though, you need in GPIO ports, port pins for and switches. I mean, this is kind of what we've done all semester. We had, one port pin, one input port pin for every input switch. But you can use, you might imagine though, if you think about the number of keys on a standard computer keyboard, I don't know, there's 40, 50 different keys there, more probably. The number of port pins that would take up just to read each individual switch on a computer keyboard. Computer keyboards aren't interfaced that way. Computer keyboards actually have their own internal microcontroller and actually just send like the ASCII code to the computer. So that's why we don't have 100 different wires running to the computer keyboard. They're actually intelligent keyboards. This is for interfacing to a dumb, and again, typically 16-key keyboard using what's known as a scanned interface. And the advantage is it can use far fewer port pins. So it wouldn't necessarily have to be for a keyboard, but any time that you need to connect maybe a large number of input switches to a microcontroller. An issue with all of these microcontrollers is the number of port pins that you have available. Right? This one has a fairly large number of port pins, but they have multiple functions. So if you start using them for SPI or UART or motor control, you start to run out of port pins, especially on complex projects. So anything that you may be able to do to reduce the number of port pins could possibly be a good thing. So the idea here is you arrange the N switches in M rows and N columns. So we'll actually make our software more complex. The traditional interface of one port pin for every switch is pretty easy on the software side. You just read that port pin to see if the switch is open or closed. Well, with the scan keyboard interface or the scan switch interface, our software becomes more complex, but requires far fewer port pins. So capital N here is M times N. And I'll put this figure up on the wall as shown, but it's in your textbook in figure 815. You only need M plus N port pins. That's not a lot for maybe 16 keys. Instead of 6 port pins in a 4x4 arrangement, you would only need 8, half the number of port pins. But that's a fairly significant savings. But in a 10x10 arrangement with 100 different switches, instead of using 100 port pins, which you don't have that many available, this would only use 20 port pins. And then there are other designs that you could possibly use. Let's see. I'll put up some code here in a minute, some example code that you could use that corresponds to this figure. I think it'll come up, but I'll continue writing over here, and then we'll go back and talk about the figure. Normally, the switches are open, at least in this figure, and then all inputs are high in the normal configuration. And then we're going to, what you do is drive one row at a time. This thing does not want to seem to work in this class. I used it this morning with no problem. Well, let's see. It would take me, let me draw a portion of it up here on the board anyway. So with the microcontroller, and then this is showing pins 0 through 3 of port 4, providing the rows to the keyboard interface. And then port pins, and the figure he's got 7, 2, 6, 5, and 4, actually providing the columns. And these all have external pull-ups. Plus 3.3. And then I'm not going to draw all of these, but then there are switches at each and then actually this would be the last column. I skipped some columns in here, sorry. So there's 2 others in here. And these are output, and then these are input. Okay. So it's a grid of switches. And so when you press a switch, he's got them 1, 2, 3, 4. You know, 1, 2, 3, A, B, C, and D. And 1, 2, 3, 4, 5, 6, 7, 8, 9, star, 0, pound. You could also use it, I guess, if you added the E and F instead of the star and pound, you could use it for hex key input. But the way, again, they're nothing more than simple switches, but the way you would do this is you drive one row at a time low. So code to do that would be, actually, we're just going to set P4.0 is output mode. We'll put the other rows in a high impedance mode. Okay, so they're essentially disconnected. The high impedance mode is also when they're like in the input mode, because the input interface is a high impedance interface. So we just set P4. So this would set just the first bit, or P40 into output mode, and then set everything else into input mode. And then the value I'd write out is, so this would send that particular output bit low, right? But send it the complement. So this would, and then leave the others unchanged, right? So on output pin 4. So this would drive this entire row, this line that's connected to 4 switches, one side of 4 switches, all low. Okay. So the idea is if any one of these switches is pressed, when we read from the columns, a 0 at any one of those locations would tell us that that corresponding switch is pressed. All the others would be high. And because we know then the row and column location, we can uniquely identify the switch. That's just for these 4 keys. And then the next time through the loop, we would send the next row low, okay, and scan, this is what's called a scanned interface. Read the input again. So we do that with, now read the input. These are the columns. So we could do that with P2N, and we're only interested in, I'm just showing what he has in the figure, which is bits 4, 5, 6, and 7. So I'm going to mask off the lower 4 because I don't care about those. And then now we could find the particular key. You could do this in a number of different ways, but if we mask with the 80 would be 100, 000, so that would be masking off this. If that is equal to zero, so it's just testing that one bit. That means that we're reading a low here. Then I could set C equal to the asterisk. So this is just storing in the ASCII encoding. Else if input would be, the next one would be 4 0. If that's low, then I'd set the character equal to a 0. It's probably not the most efficient way to do this, but you get the idea. My software becomes much more complex because now I have to loop through this, alternately setting in turn each of my 4 rows low, reading in the columns, okay, determining which column is low. That then identifies the key. And it becomes a lot more complicated if you're going to allow dual key presses or anything like that. So my recommendation is don't. Okay, this would typically detect in the whichever last key is pressed out of the scan if you have multiple ones that are pressed simultaneously. So you could put all this in a function, call it, would return nothing if no keys are pressed, but then return the corresponding key if a particular key is pressed. See if this thing's reset. So I can use it for key. Okay, actuators convert this belt works fine. It just doesn't, it's not hooked to the computer. Actuators convert energy into mechanical energy. So for us, it would be converting electrical energy into mechanical energy. So included in this are devices, relays, solenoids, motors are all forms of actuators. We will generally need an external supply, just like we did for our external LEDs, to meet voltage and current requirements. So I'll show you an example of a typical interface to an actuator. So I'm going to put an electrical model for just an arbitrary actuator. So the model has a resistance and inductance. Hey, resistance and inductance. And typically, you will need to use interface through a transistor or other device because the microcontroller itself can't supply either enough current or enough voltage. So let me just put here, maybe 12 volts here or 24 volts. You will almost always want to use some sort of interface device. And this particular microcontroller is capable of supplying 6 milliamps of current or 20 milliamps of current in the high drive mode. But typically, you'll want to use an external supply to power your device. There's one more piece here. You'll need a resistor, a base resistor here. There's another device here called a snubber diode, which I'll talk about. So current here is IA. Put this voltage across the inductor and call it current through that snubber diode IE. Now, so again, our particular microcontroller can supply up to 6 milliamps of current and 20 milliamps in the high drive mode. I think we've got these 2222 transistors, which can provide more current up to half an amp. In some cases, you may need significantly more current. Voltage is also a consideration. Devices are designed to run at particular either DC or AC supply voltages. The snubber diode protects the interface from high voltages due to switching on, off the inductor. Okay. Again, it may just be if it's part of a motor, you've got just internal windings in the motor that actually act as an inductor, or it may be, and a relay an actual coil, or in a solenoid an actual coil that forms up in this inductance. But in normal operation, then you got current flowing through your, I'll say it, solenoid here. When this thing is, when you turn on, put a high voltage here, turns the transistor on, transistor goes into saturation, allows current to flow through this device. And so in normal operation, IA is greater than 0, and then there is no current through the snubber diode. But the issue becomes, and you have to be careful of this, anytime you turn on and off current to an inductor. So when switching the actuator off, the derivative, okay, you're trying to cut the current off through the inductor. If this thing's a switch, you're trying to cut that current off immediately. So di dt is large and negative, right? I is decreasing. So dia dt is large and negative. So the corresponding voltage is negative. What the inductor tries to do is it tries to prevent the current through the inductor from changing. So if you try to switch it off, it'll generate a large negative voltage across the inductor, which tries to continue current flowing in that same direction. Well, the issue is I turned my transistor off. So now I'm trying to force current through this transistor that's off. I'll also have a very large voltage across it. The voltage here across the transistor, Vs, would be, ignoring the EMF voltage, minus VL plus 12. Minus VL plus 12, or the magnitude of the voltage across the inductor, because it's going to be negative. So this would be positive plus 12. Now, when I say that might be large, it can be in the hundreds or even thousands of volts. One application of actually switching current off and on through an inductor or coil is in a car ignition system, where they take the 12 volts from the battery. They used to use contacts or points, mechanical switches. Now it's electronic ignition, but the principle is the same. Open and close a switch where voltage from a 12 volt battery, current flowing through a coil. They open up the switch, the coil generates thousands of volts, the thousands of volts that are necessary to create an arc across a spark plug gap, to create the fire in the cylinder, okay, to ignite the gasoline in the cylinder. So you can create a very large voltage by switching off current flow through an inductor. Will cause the inductor to generate a huge voltage proportional to, the derivative of the current. So, which if I could do that, turn the current off that sharply, that would be an infinite voltage, right? So the voltage here can be very large, significantly so that would damage either this transistor, or in the worst case, if I hook it up directly to my microcontroller, it's going to destroy my microcontroller. It's another reason why it's always a good idea to use some sort of interface device, because I want to destroy this transistor. I don't want to destroy this transistor, but it's better to wreck this transistor than wrecking my microcontroller. So what does the snubber diode do? Well, now when I generate this large voltage across the inductor here with this polarity trying to force current this way, well, this is off, but now I've got an alternate current path here through the inductor. So when my transistor switches off, now current will continue to flow. It'll die down pretty quickly, but not immediately. I've got an alternate path here for my inductor current instead of through my off device. So I'll switch this off, then the diode current would be non-zero. The voltage now would be 0.7 plus 12. through this path to ground, and would be limited to 12.7 volts instead of in the hundreds of volts that I could possibly get from my inductor. So just be aware of anytime you're trying to switch on and off current to an inductor, that can cause large voltages to be generated, which might damage your microcontroller or your interface device. Let's see. Another simple device to hook up, well, is a relay. These are microcontrolled switches. Actually, they don't have to be microcontrolled switch, so they're actually just a way to, using a small current, control a switch that handles much larger currents and or voltages. But there are a couple different types of relays, maybe either AC or DC. So meaning that on the switch side of the relay, it's designed for an AC current or a DC current. And you can get them either as electromagnetic or solid state. But here's a picture of an electromagnetic relay. So typically, draw the relay itself. There's an electromagnet, and then a switch. So here's the relay. So that when I apply power to the electromagnet, the coil, it activates the switch, it pulls the switch. Now this would typically be spring loaded. That's a spring. It looks a lot like a coil, but it's a spring. You can tell by context. Okay, the spring would actually then return the switch to the open position when I deactivate the coil. So this is an electromagnetic coil. So to hook this up again, and you can get these so that you can buy these so that you can interface them directly to microcontrollers. You can operate them off 3.3 volts or 5 volts. If not, if the coil side requires, higher voltage, 12 volts or something like that, we'd have to use an interface. But I'm going to hook it up directly to my microcontroller. Because I'm hooking up to a coil, though, I want to get the snub. I have to use a snubber diode to protect my microcontroller. And then here, and current would normally be flowing this way. When I switch this off, I'm going to generate a large negative voltage here, which would damage my microcontroller. I want to allow an alternate current path, so I hook up a snubber diode that way. It often looks backwards, right? But that's because in normal operation, it's not supposed to carry current. It's reverse biased. So normal operation current flow is this, and the diode acts like an open. But as soon as I try to switch this current off, I'll generate a large negative voltage here, which would continue to cause current to flow in this direction, draw current from my microcontroller. But now with the diode here, it would actually flow in that loop. And it would ensure that the reverse voltage across the microcontroller then now would be limited to negative 0.7 volts. Right? Because this would be plus minus 0.7 when I turn that inductor off. So make sure that voltage would not drop below negative 0.7 volts. Now, but this would typically be for, with a solid state relay, you wouldn't need the snubber diode. It doesn't use the electromagnetic coil. But the idea here is now I can control, a light, a motor, something designed to operate off of does that look like an electrical plug? Off of 120 volts AC. So I can use my microcontroller and a little relay to turn off, a lamp or something like that electronically, or a motor or whatever. You can, and there are unfortunately thousands of different options, depending on the switch type, what they call single pole, single throw. I think we looked at switches earlier in the semester. Whether it's normally open, which means when there's no power applied to the coil, the switch is in the open position. It's normally open. You can get it so it's normally closed, so that even with no power applied, this switch is closed, which in that case means that the light would be on, and then I'd have to activate the coil to actually open it up. So either configuration, or with multiple switch types, this would be a single pole double throw, one pole but two throw positions, with 3 terminals here. So you could use it either as normally open or normally closed. And then last thing I'll mention just briefly are solenoids. And this term will be used differently depending on context. Usually in electrical engineering, a solenoid refers to a device that converts electrical energy into linear motion. So often it's just a coil with a movable core. It's a magnetized core, so that when I activate the core moves in one direction, either right or left, just due to the interaction between the electromagnetic fields of the permanent magnet and the core material and the electromagnet produced by the coil. So this could be used in like door locks, or for disk drives, for ejecting disk drives or tapes, any sort of ejection device. Seen them used on assembly lines to actually kick parts off of an assembly line. Often, when activated, it moves in one direction, and then you have to have a spring to restore it or something after, then you would depower it. And typically, for connecting to a solenoid, you're going to need some sort of interface. You're not going to be able to connect it directly to the microcontroller to get the voltage and current that you need. So that's all I have today. You've got a little bit of time to finish up on the LCD interface. Was everyone able to follow the software download? I have a software up on the website. So you have to make sure you can get the software downloaded into your project and the project to compile. There still apparently is an issue with the software. So we'll try and track that down. But make sure you've got the hardware interface, and I'll see if I can't see what's going on with that. I'll put up that picture I had last time showing so the software is all on the website. I have a picture of that. No, I could.
Yeah, I even put the black light, or the backlight to it.
Yeah,
And that didn't work.
Yeah, I think what I read, the backlight is will draw a lot of current, can draw a lot of current. I mean, you had the resistor in there to limit the amount of current. But I don't think that's not necessary. You shouldn't be able to, it'd be necessary if you're trying to read it at night, but in daylight, it's not necessary. But there's some other issue going. There's a bunch of different of these little Nokia displays that are sold by different manufacturers. But I think ours actually match the one figure you had in the text. So I suspect there's something with the software. I don't even have one connected here. So. Oh, in the other thing, user's guide. So in the user's guide for the launch pad, so if you're like me and put the cable tie over the header labels so you can't read them. This is not that. It's actually in, let me bring up the Code Composer Studio. Like I don't have the user's guide for the launch pad itself downloaded here. Or do I?
Oh, it would say on the back. I didn't know it was there.